Okay, so what we've been doing the last few lectures is we've been trying to understand what Haskell is on about when it talks about functors and things like this, right? And we tried to show you that it's not just something that Haskell made up, it's actually coming from a coherent theory, mathematical theory, and it extends beyond what Haskell is doing. And in Agda, we can actually talk about these things, and it's a good way to structure our programs in general, just beyond what Haskell is doing. So today, we're going to try to extend this propaganda beyond functors to monads. So remember, in Haskell, there is such a thing as a monad type class, which, okay, it's defined a little bit differently nowadays. So it used to be that if M was a functor, then M could sometimes be a monad, and you had to have certain operations, which we've already seen, of course, when we have been doing these things in Agda, the maybe monad, for example. So today, yeah.
I was going to say, yes. So applicative is a superclass of monad, but functor is a superclass of applicative. So you definitely have to be a functor if you're a monad. The other thing we notice is that we're only talking about things that map Haskell types to Haskell types. So we're talking about monads for one particular category here, not what the notion means more generally.
Yeah, but it does make sense more generally, just like functors make sense more generally, right? So the point of today is to see what it means more generally. So let's just do that. We can start with the definition, and then we'll try to give you some intuition, and then we'll give you some examples, and then that's probably plenty for today. So let's see if we can talk through the definition. So we're saying that what does it mean to be a monad for some given category? Well, first of all, you have to be a functor. That's what Connie just said, right? That in Haskell, functor is a superclass of monad. So we're talking about certain functors being monads or not, right? A functor is a monad if you have some extra structure. And because of the type of this extra structure, which we'll see in a moment, it only really makes sense for functors that go from a category C to itself, not from a category C to a category D. You can have some fun trying to generalize this, but the standard notion only makes sense from C to C. So you have a so-called endofunctor on C. And now you want to say that this is a monad. And what's the intuition? Well, it's a little bit like the thing we had with monoids, right? You notice that monad and monoid sound similar, and that's not a coincidence. It's this idea that we would like to take the functor applied n times and squish it down to the functor applied one time. And the intuition we have for monads is that this is a kind of effectful operation. So we say that if you have no effect, then that's trivially effectful. And if you have two effects, then you can chain them together to make them into one effect. Right?
Just A. The same as just A, or is it nothing to nothing, right?
It's not necessarily the same as, but
we can
transformation.
We can squish it together into
yes. So the sort of general idea that you can always get your hands on one of these things from any number of these things, any number of layers of M in this instance, because if you have no layers of M, there's a thing you can do to get one. And if you've got more than one layer, there's a thing you can do to squish two of them into one. And then there are some laws which say it doesn't matter what order you do that in.
So we'll go through this in more detail, of course. But so this is one of the reasons why we wanted to introduce natural transformation, was that we wanted to talk about how to go from nothing, the identity functor, into M, and how to go to M composed with M. So that's like two layers of M, right? M of X into just one layer of M. So we need to be able to say what is a map from M of M to just M, and that's exactly a natural transformation, right? So what was a natural transformation? It was a way to turn M of X into M of X here in a way that commuted with the functors, right? It doesn't matter if you if you apply a functor before or after you do the transformation. That's the naturality.
And that's to say that we're only rearranging the superstructure.
Yeah.
So here somehow we're kind of doing some wrapping of stuff, but leaving the stuff alone. And here we're squishing outer layers of wrapping, again, leaving the stuff alone. Yeah, is it worth trying to give some intuition about computations, or is that?
No,
something
I
to
think
do
that's
later?
good. Go for it.
Okay, so I sometimes like to think of such an M as, in my head, it's plan to get a, right? M of X is a plan to get an X. So this says, if I already have an X, then I've got pretty smug plan to get an X. You know, just use the one I've got in my hand. And what this says is that if I've got a plan to get an X, I've got a plan to get an X. Because I can first of all do some work to get my plan, and then I can do more work to carry out that plan. So that's the key characteristic of monads, is that they allow you to compute a computation. They allow you to do some computation to figure out what computation to do next.
And also notice, as you might be familiar with from Haskell, that you can go from X to M of X, but in general, you can't go from M of X to X, right? Just because I have a plan to take over the world doesn't mean I can actually take over the world.
Yes. So that's the thing. You always end up at 1. That's the mon bit in monad. You can go from nothing to 1. You can go from more than 1 back and down to 1. But you can't go from 1 layer of M back to 0 necessarily.
Okay, so that's these two. So we have the return, which turns 0 into 1, and we have the join, which joins 2 layers of M back into 1 layer, right? And then we have some laws for these things, which tells you what happens if you combine return and join in different ways. And there's 2 ways you can motivate this, I think. So we'll motivate them one way today. And then another way to motivate it is that this is exactly what you need in order to make the so-called Kleisli category, where you make a category where the functions, the morphisms themselves, are effectful functions. But I put that at the end of this file, but I don't think we'll get to it. So, so what do they say otherwise? So they say that if you think of this as really squishing things together, then they express that there's really only one way to do it, right? So for example, the first one here says that if you first take, so this is the return, that's the one that turns 0 things into 1 thing. But if you start at M of X already, so you're turning an M of X into an M of X, kind of artificially, right? Because the return is the thing that just embeds no effectful thing into effectful things, but it could happen that you start at M of X, right? So then you end up at M of X, and then you could apply the join to squish it back together again. And then this law says that actually that's not doing anything, right? If you're adding a trivial computation, then that's not doing anything
If
at
you
all.
have a boring plan to get an X, and you squash those 2 layers, you just get the plan that you first thought of.
But you're only getting back to M of X, right? So this is not actually breaking out of the plan.
Yeah.
And the second one similarly says, well, if you start with just an X and you make a M of X from it, but you're doing this inside of an M. So that's what fmap M means, right? Fmap M means do something inside M. So this goes from X to M of X. So this thing goes from M of X to M of X again. And then if you join this together, that should still be redundant because you're still just doing trivial things inside of the thing.
Yeah, so what happens, we started with a plan to get an X, and then we turned it into the plan to get an X and then do something boring to have the same X. And then we combined those layers. So this time, the extra layer of boring arrived on the inside rather than the outside. And we just say, squishing a do-nothing layer leaves you with the other thing, the other layer. So note, this is the identity not on X, but on M of X.
Yeah. So this is saying what's happening if you first return and then join in the two different ways you can first return. You could either do it on the outside or on the inside, right? And the last one says what's happening if you join twice.
Yeah. It says if you've got 3 layers of M, right, so you've got a plan to get a plan to get a plan to get an X, and you could squish together either the outer 2 layers or the inner 2 layers first, leaving you with 2 layers somehow, and then you squish together the 2 layers you've got left. You can think of this as really saying, intuitively, this is really what you're used to in your entire programming life as the associativity of the semicolon, right? Do this, then do that, then do the other, right? Doesn't matter how those semicolons nest. It's just a program made of doing 3 things.
So comp is the composition of the category, right?
Yeah.
So it's saying if I first do this and then I do that, that's the same as first doing this and then doing that. I talked for too long. Right.
But join has to take it to.
Join takes one thing with 2 layers.
So join goes from M of X into M of X. Right.
So it doesn't take a pair, it takes one thing with 2 layers.
But there,
It goes from the composition of the functor.
but there you do the join at them.
Yeah, so that's saying, so this goes from M of whatever this is. So this is another M, so that's 3M. Right. So this is saying that, okay, there's only one way to join 3 layers. And this is saying there's only one way to join 0 layers. Right? So then overall, there's only one way to join n layers, right? By combining these. Okay, so we should probably look at an example. Because as usual, you have the definition, you can kind of understand why it works, but as almost always, the important thing is defining the data, which are these natural transformations, right? How to make a trivial thing, how to join 2 non-trivial things. And then you just verify that you check these, and then you just ask Agda for the types of the things you need to check. Right? So the important thing is thinking of these things, that there is one way to turn an X into an M of X, and there's one way to turn an M of X into an M of X. Right? Sorry, now we said M of X 10,000 times. So here's one example of a monad, which is our favorite racer.
This time, we start with numbers and adding up, but the extra programming language feature we're going to explore is variables.
Yeah. So on top of it, the other things I've added in one more constructor, which says that if you have an X, then you get an expression, which is the variable. And I'm parameterizing all the expressions on the set of variables I can refer to. Right? So that means that I have a chance of making X per itself into a functor from set to set, right? Because it takes a set in and it gives me back a set. And right, so what does it mean for this to be a functor? Well, it means that if I have a function from X to Y, I should be able to lift that to a function from expressions with variables in X to expressions with variables in Y, right? So I pre-cooked some of these things because we've done this over and over again, so I'm hoping we can get to the monad part.
Right. So in this case, what the functor action gives you is exactly renaming for the variables.
Yeah.
Right.
Because you see that the only place you actually have an X occurring is in the variables, so that's where we apply the function. Everything else we either keep the same or we just do recursive calls, right? Right. Yeah. Sorry.
Yes.
That's just me
Yes.
pattern matching on X. Yes. This
Yeah,
is in my mind.
that's a
That's
prudent bit of alpha conversion.
yes.
Um,
Yes. Good
and
point.
same thing will happen down there.
Right down here. Yeah. Okay. So we defined these expressions. We shown that there is something that lifts a function to a function on expressions, and then that means that we can turn it into a functor if we are lucky, where we say that the action on objects is given by this expr, which given a set gives us a new set. The action on morphisms, the fmap, is given by this function. And then with not too much difficulty, you prove that it satisfies the law. So it preserves the identity.
Yes, given that map does stuff to the variables and nothing to anything else, then mapping by the identity does nothing to the variables and nothing to anything else.
Yeah. So it's the usual just proof by pattern matching, where the only interesting thing is what's happening here. But then, like Connie has said, if f is the identity, then nothing happens. If f is a composition, then it's a composition on both sides.
What's COM2?
COM2 is COM, but for a two-variable function.
Okay.
So this says that if the left-hand sides are equal and the right-hand sides are equal, then the whole thing is equal, right? And this is the proof that the left-hand sides are equal. This is the proof that the right-hand sides are equal.
Yeah, bad library design.
Okay, so we have a functor. So now we could try and make it into a monad. And I again pre-cooked some things, but let's get back to them. So if I want to make it a monad on set, then first of all I have to say what the functor is. And I said that this was supposed to be expr. And then here now I have to give a return for my monad and a join for my monad, right? And these are natural transformations. Let me make that bigger. So if I don't remember what these are, I can pattern match on the goal, and I'm reminded that I have to give a transformation and prove that it's natural. You can look at the type of the return. Well, so it's supposed to be a transformation, so it says that for every x, I should be able to go from x to expr of x, right? X here is the identity functor applied to x, right? So it's a transformation from ID into expr.
Right. What that's saying is, if we have a variable, can we construct the expression consisting of exactly that variable?
Any ideas?
Also, sorry, you chose num-x with the second level of
Yes, of course. Good point.
Right.
Well, that's exactly what the variable constructor is doing, right? It's taking an x and giving me an expression.
It's almost as if we did it deliberately.
You don't like that.
Okay.
Okay, and now I have to show that this is natural. What does that mean? It means that if I apply a functor and then I apply the
Yeah, it's already too normalized.
Yes.
It's just done the business
right,
for
maybe
you.
it's easier if I don't.
Right. You know, what map does on var is exactly apply the function to the variable.
Yes, so that's why it's easy in this
so,
case. Right, so it's saying if I first map with the identity functor and then I transform, that should be the same thing as if I first transform and then map with the expr functor.
Yes. Yeah,
Yeah.
exactly. Because this map, because transform is var, a map just computes straight through var to give you this.
Well, on this side actually, right? So on this side, the identity
yes.
functor is just f.
Yes.
So that's going to turn an.
Okay, no, yes, I'm reading composition backwards. Yes.
Yeah.
Okay, it's this side. So yeah.
So on this side, we're just going to compute straight through the var, and right.
Yeah.
All in all, we get something that's really easy to prove.
Right. However, the next one will be more fun.
Right. So here, again, it has to be a natural transformation, so we have to give a transformation which is natural. So that now means that we should go from m of x to m of x, right? But m here is expert, so we need to take an expression where the variables are themselves expressions and turn that into an expression, right? To be able to squish 2 layers of expression down into 1 layer of expression. So that's exactly what I suggest that we do in a helper function up here, right? Well, Connor scribbles on the board.
Sort of.
So not in this formulation, right? But this thing down here is substitution, but we will get to that. So this is saying if I have an expression, and then when I get to the variables, I already have an expression, then, okay, it's a little bit like substitution, right? Because then I should be able to just slot it in, but let's see. So what can I have? The expression I have is still a variable or number or a plus, right? And the interesting case is exactly when it's a variable, because then the e here is itself an expression, so I can just use that as my new expression, right?
Right. So what I've drawn here is a picture of an expression where the but it's a 2-layer expression. So I've just drawn a box for the use of the var constructor. So you can see in my outer expression what's in my variables, my red boxes. And in those red boxes are some inner expressions that have got black boxes for variables full of some other variables. So I've got expressions whose variables are expressions of variables. And what join is going to do is erase the red boxes. Oh yeah. Yes. So that's, join is just going to merge these down into one expression by erasing the red boxes.
Right. And that's exactly what we're doing here, right?
Yes.
The red box is the variable constructor, and we are not keeping it on the right-hand side.
So could we prove that there is a Monad that do an isomorphism between x?
Yes.
Yes.
We can do, there's a fairly epic maneuver of which that is a special case. Yes.
Okay, so we've done the interesting case where it looked simple enough.
Yes.
And now the rest of it just boilerplate, right? In the sense that if I have a number, then that's still a number even if I change my notion of variables. I can use the same n.
So this is the programming version of erase the red boxes, where the thing that I'm not saying when I say erase the red boxes is keep everything else as it was. Yeah.
You see the free stays the free, and the plus stays a plus, right? So this is something plus something, and then I just keep erasing the boxes in the sub-expressions, right? Okay, so that's the operation. And I think it's a good idea to leave it as a separate helper function, because next we're going to prove something about it, right? So here. No, not really. This is completely first order, right? There's no function types anywhere here. Okay, so what do we need to prove? Well, we need to prove that if we first map in M composed with M, and then join, that's the same as first joining and then mapping, right? So get an X and a Y and an F.
So one of these should be easy.
We're still just doing naturality. So,
right, yes. Okay, no, that will take some work.
So, right, so what am I saying? I'm saying that, again, I want to prove that two functions are equal. REFL is not going to work because this doesn't look exactly the same. So I'm going to use extensionality. This is fully normalized, right? Because map expression is going to look at the x, and the join is going to look at its argument. So
Yes. So this is classic. Why is it stuck?
Yeah.
But you can already predict. We've just seen that that both map and join preserve everything but the variables. Or rather, everything but what happens at the variable constructor. Map even preserves the variable constructor and acts underneath it. Join erases the variable constructor. And correspondingly, we are going, this is an absolute candidate for a boring inductive proof, where the variable case will be the interesting base case and everything else will just be rewrite by the inductive hypotheses.
but we can kind of just not worry too much about it, right? I mean, we do what we always do.
Yes.
We saw it was quality of function, so it's xed, and then it wasn't obvious because then we wouldn't have needed the xed. So we just break it out into a lemma and start pattern matching, right?
Yeah. But we already know.
I'm going to call this E.
Could you turn it into a path map?
No, they're not
because
recursive.
I want
We're
to do a
gonna-
recursive call, right?
Oh,
So
Yes.
and a lambda is anonymous, so I can't do recursive calls. Right, so pattern match on E.
Right. So we're hoping for. No man. We're hoping for. Yeah.
Right. I mean, in this
Well,
case,
actually, var e is good.
because it is an expression, but yeah.
Yes. And
Okay. So
arguably, these should be EE and EE
Right.
prime.
right. Fine, Mr. Cummings. Yeah.
Yes.
Okay. It doesn't change the fact that I'm just going to say REFL here.
Yeah.
Right?
Yes. So we're expecting it. Right. I mean, it's splitting hairs to say that that this was inevitably boring REFL, whereas
This is an interesting REFL.
the first one was interesting because it
Yeah.
required an actual compatibility between map and join.
Right. And then here, as always, I know I need to do some kind of recursive call, so I'm going to rewrite by both recursive calls and see where I end up.
Could you call two?
Yes.
Well, we can see, right? Yeah, because if we look at the goal, we say both of them are pluses.
Yeah.
So indeed, I could have done a com2 of the things, which is maybe the nicer way to do it. But now, after the rewrites, I'm in REFL territory again, right? Okay, so join is natural. And now we still have to check these laws for the monad itself, and some of them are going to be reassuringly boring. So this is saying, well, if you first do a var, that's return, and then you join it back down again, then you get the identity function. Right?
Yes. So this is the situation where you have a red box containing stuff, some tree, and erasing the red box directly. If the red box is on the outside, just straight away.
Yeah, you start with a
Get your
tree,
tree.
you draw a red box around it, and you delete the red box.
Yes.
Surprise, you ended up with the same tree.
Yeah.
Okay, so what about the next one? So here, something more interesting happens, right? So we still wanted something to be equal to the identity, but this time we said that, well, if you first map with the return, the var constructor, and then join again, that should be the identity, right? So here refl doesn't immediately work. I'm kind of going to show you what this is.
Right, so if you've got your tree with the red boxes, and then you draw black boxes inside the red boxes directly, and then you erase the red boxes, you get back the same tree. That's what's happening. So this time, the extra layer of boxes goes on the inside, so we have to dig through the tree to find where the action is. But we're still doing something essentially trivial.
Yeah. But we do have to do another proof by pattern matching, right? So again, same story, two functions equals, I'm going to use ext. Then I'm going to do this. I should really use the Control-C, Control-H thing, right? But
rummage. Excellent.
So it's a different x. X is really universally quantified here. If I look here, right, see that there's an x which is not in scope. So yes, I could bring it in scope here, but this is true for every x anyway, right? So okay, so I'm going to pattern match on the x. And then I'm going to look at what I need to prove. And in most cases, it's going to be bored. So this now says var x equals var x. Why is that? Well, x is var x, so that's the right-hand side. And here I'm mapping var over x, so that's var x. And then I'm joining, that's var x, right? X was var x. And then joined was removing the outer box. So this becomes refl. And here it's easy. And here it's going to be another case of just doing the recursive calls. Let's do it with a conc2 for fun. Okay, and what about this one? So this said that if you were joining and then, what was it? It's joining and then joining again. It's the same as joining on the inner side and then joining again.
Right, I've cooked up the right picture while you were doing the other proof. So it's here where we've got we start with 3 layers. So my outer vars are represented by blue boxes, my middle vars are represented by red boxes, and my innermost ones are represented by black boxes. So on one side of the equation, the join side, that corresponds to erasing the blue boxes, then erasing the red boxes. On the other side of the equation, we first of all map join across the structures. That means we do join inside the blue boxes, which is the same as saying we erase the red boxes and then we erase the blue boxes. So it's about the order in which we erase blue and red. And we're saying, well, it doesn't matter whether we do the blue ones first or the red ones first.
It doesn't matter if you're colorblind or not either.
Well, I was glad to find a blue pen because I suspected my bag contained only a green. And I don't know if anyone in the room is red-green colorblind. But
well, the point is that it doesn't matter because it's the same. Anyway.
Yes. Yeah, unlike, for example, yeah, my brother's red-green colorblind, and I remember one time he phoned me up and said, I think my tomatoes are ripe. Can you come and pick them for me?
Well,
Some of them were, but you needed not to be red-green colorblind to pick the right ones.
Okay, so I'm doing the same moves again. Quality of functions, do a helper function, pattern match on the X, rename everything inside. and look at interesting cases. So that looks like it's okay. And the rest of them are going to be boring. Right. So we managed to define a monad. And it helps to think about the picture. But if you don't want to think about the picture, you do get quite far by just asking Agda what you need to prove and then proving it. Right. Right. And then we had Jake's question about substitution. So substitution for expressions would look something like this, right? It's saying that if for every variable I have an expression, then substitution would say that if I then have a whole expression of things, I can use this function on all of the variables in order to get the whole expression, where I've changed my variables to be y's instead, right? And you see that you can get that by mapping this thing and then joining.
Yes. So first of all, you replace each variable by its image, and that gives you a two-layer structure, which you then squish down.
Yeah.
So after the map f, you've still got red boxes.
Yeah. So
you've replaced the variables in the outer term by some new expressions, but now you need to graph them all in to make one big expression.
And it's not a coincidence that you can derive this bind from join and map, right? You can always do this for any monad. And it's an equivalent way to give the monad. So that's exactly why in Haskell land, this is defined with the bind as the primitive operation. And then from bind, you can derive join, right? Oh, maybe you need, do I need control.monad for this? You see that the join is exactly m of a into m of a, right? And Haskell does it the other way. They start with the bind and derive the join. But for the thing we're doing next, it's more straightforward to start with a join and derive the bind if you need it, right? So, but these.
I very much right at the start. What do you think of the bind? So it's a special case of bind.
It's a special case of bind where this thing is not is ignoring its argument. Yeah.
Yes.
So it's I don't know how to pronounce it, but it's the thing if in a do block, if you do a do statement and you don't bind the result to anything.
Yes.
Right.
So it does have an informal name, which is misleading. It's the thing that behaves like semicolon.
Right. Because it's
just this then that.
It's run this effectful thing, then this effectful thing, and overall you get the result of this, the B, right? Okay, let's look at one more example. So this was perhaps a little bit misleading because it was still a monad on set, right? So it looked a lot like what you could do in Haskell. But we said that monads make sense in arbitrary categories. So let's look at a monad in preorders, where if you have a given preorder, then I would like to add a bottom element to my preorder, because the preorder might or might not have a minimal element, right? So I'm defining this new data type where I include all of the old things, and I'm adding a new bottom that I intend to be the smallest thing. And I have to put the prime here because bottom is already the empty type. And then I have to define an order on this new thing, right? So I want to lift the old order. So it should be an order on, right, this is the order on the lifted thing, right? So I'm saying that if I have two old things, then eta of p should be smaller than eta of p prime if p was smaller than p prime in the original order. And I'm adding in one new constructor which says that bottom really is the smallest element, right? So bottom is smaller than any x. Okay, and if I want to make this into a preorder, I then have to show that this is reflexive and transitive, right? So let's prove that. So what does this mean? It means that for every x, x should be less than or equal to itself. And how do I prove it? Well, I can pattern match on the x, right? X is either going to be an old thing included or the new bottom, right? And if it's an old thing included, then I have to show that eta of x is smaller or equal to eta of x, but I have a constructor for such things. And now I need that x is smaller than x, but I started with a pre-order, so I know that it's reflexive, right? And if I want to show that bottom is smaller or equal to bottom, well, bottom is smaller or equal to anything according to the thing I defined. So that's easy. And similarly, if I want to prove transitivity, I get the proof that x is smaller than y and a proof that y is smaller than z, and I want to show that x is smaller than z. So I pattern match on both proofs. And we see that there's 3 cases. They could both be old proofs, or they could be a bottom here. And I think actually I don't need to do these 2 cases separately, right?
All those ones won't be trivial rather than that one.
Because the fact that I have a bottom here means that x must be the smallest element. So the thing I have to prove is that the smallest element is smaller than z, right? In this case, P Q. Then again, I want to show that 2 old things are related. I have a constructor for that. And now I need that. Okay, the names are terrible here, but I can use transitivity of P to go from here to here and then to here, which is what I want, right? Okay, and in the same way, you can define a map function, which if you're an old thing, you apply the function, it preserves the bottom. So that makes it into a functor after you prove some small things again. Let's see if you can make it into a monad.
Why is the function going from x to y set of those products?
Which one? This one. So this is the, yeah, I'm saying that the underlying function of fmap is this map lift.
Yes. So if someone gives you a monotone map, then lifting it that way will be monotone.
Yes, but this is the more monotone map.
Yes.
Okay, cool.
Yeah. Yeah, I mean, I don't need that the f coming in is monotone in order to lift it, right?
Oh, okay, yeah.
But then in
So
the
you
next,
always define
Well, so yeah, so when you're doing these sorts of things where you've got an underlying carrier set and then some extra structure, you know, inevitably there's the programming bit is just going to work on the underlying carrier sets.
okay, so this is my functor, and then I have to define return and join. So return, well, for every preorder P, we need to define a monotone map from P into lift of P, right? So what does that mean? There has to be an underlying function, which should go from the carrier of P into lift of the carrier of P. But that's exactly what this constructor is doing, right? It's embedding all of the old things. So this. And I need this to be monotone. Well, it says that if x is less than y, then eta of x should be less than eta of y. That's exactly what this constructor is doing. Me too. give it some things probably, right? Right. So by construction, eta was monotone, right? But it was quite natural to say it was monotone, right? To say when are all things related. And is it natural in the other sense? X, Y, F. Right, so this is saying if you first map in the identity, so that's just F, and then you transform, that should be the same thing as if you first transform and then you F map with left. Right. And again, there is no way around proving this. Well, we have this way of proving that two monotone maps are equal, right? Then after we do that, we see that actually life is easier. What about the join? And then I think we'll stop.
Yes.
So this says for every preorder P, you have to make a monotone map from lifting twice to lifting once, right?
So we've got.
So what is the underlying function? Get an X. And what can we do? Well, we can pattern match on the X to see if it's the bottom element or not, right? If it's not the bottom element, then it's an embedded lifted thing, so we can just return it immediately. It's not a case of just removing the red box in a way, right? And if it is the bottom element, then there is a canonical way to send it to. We can send it to the bottom element again, right? What else can we possibly do? And if we didn't, then we will be in trouble because we want this to be monotone now, right? So we need to send the smallest thing to the smallest thing. So this is the bottom of the lifted lift, and this is the bottom of the lift.
Should be consistent.
Okay, so to prove that it's monotone, I can once again pattern match on the proof that X is less than Y, because I know that there's two things it could be. It could either be an embedded proof that some should probably just remove the dot. So the dot means this is determined by the other thing, right? Okay, so in this case, I can again peel off the proof. And if it's bottom, then because I sent bottom to bottom, then again, I have to prove that bottom is smaller than something, which I can do with my constructor for that. Right. Connor, you have a picture you want to give us?
So what's going on here is that the doubly lifted one is my picture on the left. So we glued on a bottom element, that's the blue one, and we then glued another bottom element under that. And well, actually, maybe I should draw this thing in blue. What's going on here is that we are merging these two bottom elements. So we're mapping that to that, and then everything else stays put. So, and so on.
So we are merging them in the sense that we are both sending them to the bottom element, right?
Yes.
But there's no way to go back, you see, because you don't know if you want to send that blue on the right to the blue on the left or the red on the left, right? So it's really only a one-way map.
Yeah, but crucially, it's so clear that this is not just a thing we can do, it's also monotone.
Yeah. Okay, so I would suggest maybe we stop here and I'll leave the rest of these as exercises, because it's again one of these things where you have a good idea how to define return and join, and then you just verify that they satisfy the equations. But the equations are there so that it plays nicely with other things. So we will do more of that on Tuesday.
Is this a special?
Yes, we'll get there. So you can notice that this is kind of factoring through pointed sets. Yeah. Pointed preorders. But yes.
Yeah.
But it's more than that, right? Because it's the bottom element. It's not just a random point. We're adding a. Yeah.
Oh, I guess you
Well, it's more. Yeah, it's more useful because. Well, not necessarily. I mean, think of for example, the rational numbers. They don't have a bottom element, but it's a total order. All right, where everything is right. Yes, sure. Exactly. But that's basically the same as a set anyway. Right? Okay, let's stop here.